My name is Lauren Jones, and I'm going to be talking about internal fluid flow, which is topic 5. So I have here this system in which water is pumped from a holding tank to some higher elevation. And in this problem, we have to consider the friction loss effects. And so the first thing we need to do is determine if flow is laminar or turbulent, because the fanning friction factor here is calculated differently depending. As you can see in our equation for the friction factor of turbulent flow, we have this coefficient of roughness. However, that term is not in laminar flow. So our first question is, why doesn't the friction factor for laminar flow depend on the roughness of the pipe? Well, that's because, as you can see here, laminar flow is very slow. The flow is very uniform, and as you can see, it's moving directly along the pipe, and it really doesn't have any other motion in other directions. And so as it encounters any bumps, it's slow enough to just creep over those bumps, and it's not fast enough to be projected into any other direction like turbulent flow would. Another interesting thing about this equation for turbulent flow is that we have our friction factor depending on Reynolds number, and we have that for both laminar and turbulent flow. However, for turbulent flow, if the Reynolds number gets high enough, if the flow gets more and more turbulent, then this term here will essentially go to 0. And so what we can have is, for turbulent flow, if the Reynolds number is high enough, then the friction factor no longer depends on that Reynolds number. So why is that? That's because this term essentially represents the laminar sublayer that exists between the turbulent fluid flow inside the pipe and the walls of the pipe. So as the flow inside the pipe gets faster and faster, we're not able to withstand that laminar sublayer. So the layer gets thinner and thinner, and if the Reynolds number gets high enough, then that viscous sublayer gets thin enough that we can essentially consider it negligible. So a third conceptual question we have related to this system is, what we've done is we've assumed that the velocity of this fluid is constant throughout our entire system. So why is that if we know we're losing energy? Well, it's because through conservation of mass, we know that the mass at point 1 must equal the mass at point 2. And through continuity, we know that the density times the area times the velocity must be constant at those 2 points. So because water is being treated as incompressible, we have a constant density, and we also have a constant area of the pipe. So therefore, our velocity must also be constant, and the energy loss we see in this system actually comes in the form of pressure loss.